안녕하세요. Good morning. Good morning. 네, 안녕하세요. 네, 안녕하세요.
Recording in progress.
네, 안녕하세요. Okay, so thank you for coming to the class, even though it's a national holiday. Let's begin. Give me just a second. All right, so if I remember correctly, I think 27 or 28 people were interested in having a real-time class, so we are missing about a couple, so I think they'll come a bit late. So I think we can begin anyway. Okay, it's a little bit laggy. Let me see. What? Oh. Sorry, could you give me just a second? I actually think I need to reshare my screen. Something's wrong with me. Wrong with my good note. Yeah, I'm sorry. Yeah, just give me a second. Okay. No, when I'm yeah preparing my material, if you have any question regarding autoencoder, please feel free to ask away. Because today's material, which is variational autoencoder, is pretty much, if you, in one way to think about it is you can just view it as a simple extension to autoencoders. So if you don't know what autoencoder, if you still don't have a clear understanding of what autoencoders are, then today's material will be really hard to catch up. So if you have any question, don't be shy and please just ask. All right, I think we are ready. I think it's a little better than before. Okay, I think we'll have to begin regardless. All right. So today's topic is generative autoencoders, so how to generate new samples using just, vanilla autoencoder. If you remember, autoencoders are just for compressing stuff, right? Compressing images, and what is what we learned last week. But can we use that compression mechanism to generate new samples? So that's the first thing we're going to talk about, and then we'll move on to variational inference before going into deep diving into variational autoencoder VAE. So variational inference will be used is a technique that will be heavily used in variational autoencoder and also variational inference itself. So VI itself is also very useful just to know what VIs are, because it's widely used in a lot of machine learning, like machine learning studies and subfields, especially Bayesian neural networks and stuff. So we're going to talk about variational inference, then move on to VAE, and then lastly, a little bit of training trick that we're going to have to use. So VAE itself, variational autoencoder itself, is it's a nice theory and a great framework, but how to actually train it using PyTorch or like TensorFlow or any autograd packages, you need some trick to actually make it trainable, which is called reparametrization tricks. So we're going to learn that and then finish the class. Oh. All right, generative autoencoder. So as we've all learned this last time, so it's just that we have some sample going into the encoder, encoding, which is to compress this raw 784, example, 784 dimensional input into a 4-dimensional Z, which is sometimes we call it code or latent variable or latent representation. And then after that, using this Z, we want to decode it or decompress and get the X prime out. And we want the X and X prime to be as similar, as same as possible, right? And yeah, the architecture was pretty simple. In the simplest form, autoencoders can be implemented by using just one nonlinear transformation for compression and one nonlinear, again, another nonlinear transformation for decompression. And that's it. And the loss function would be for mean squared error. And because of the information bottleneck, we said that the most distinguishing features across samples will be stored or will be learned by the latent space. And this was our example of how different digits could be transformed into a 4-dimensional vector. And I've noted that these two should be similar in terms of its values as opposed compared to like these two or these two, right? Because they are ones and this is a 5, right? So, and because for visualization purposes, I said that we can further further compress this 4-dimensional vectors into 2-dimensional vectors so that we can scatter plot on 2D plane, right? 2-dimensional vectors using algorithms such as PCA or tsne or UMAP, so that we can scatter plot them on a 2D plane, and then we can see that there are clusters here and nicely clustered here, but not always, right? They're like 7, 4, 5, 7 or 6, 0, 2 or 8, 3. Like these are like a bit mixed up. So the question is, how can we generate new samples from our trained autoencoder? So our trained autoencoder our encoder is trained to convert a 784 dimensional input into a 4-dimensional latent space, and then it's able to decompress it back to 784, and that's it. And somehow its latent space has learned the optimal, well, hopefully the optimal space that can help your decompression process, right? And it would look something like this. Not exactly this, because this is a 2-dimensional projection of the actual 4-dimensional latent space that your autoencoder has learned, right? So this is just a projection, but it would look something similar to this. So how can we generate new samples? So one way to do it is simply just look at one of the, so right in this region here, this region here, all these dots are different ones embedded into a 4-dimensional space, right? So these are like Z1, Z2, Z3, Z4, Z5, right? These are all different Zs, but they're all ones. They're all different ones. So what we can do is we just take one Z and then slightly perturb it. For example, if we can add new dot here, which is only like this much. Isn't this a little bit? Oh, okay, I can. All right. So if we put a new dot here, then it's only like small distance away from the actual one, this one, right? So we can assume that this is probably a 1, or even better, we can interpolate between, for example, like we take this guy and this guy. So this is Z1 and this is Z2. And then what we can do is we can just interpolate between the two. So any dots on this line, this interpolated line, like dot here, dot here, dot here, these are all like this, they will all be probably like looking like a one because this is a one and this is a one, and we're interpolating just between the two. So probably this, they're all like ones. So that's another way to do it, right? So there are a couple of tricks we can use to use a trained autoencoder to generate new samples. Oh yeah, or we can just sample random. We can just get a new random point from this area. So we can just choose any one of this to be a new sample, but that wouldn't be actually generating a new sample. That would be just copy pasting the existing ones, right? Because we already know that this, like this one, this one, this one, they're all actually ones. So in order to create a new, truly new sample, like as I said, we could probably just perturb it or interpolate. That's like two like straightforward ways to do it. But that wouldn't always guarantee that you would get a nice one. So yeah, both are not really guaranteed to work because, for example, if you perturb too much, then it will not look like a one. For example, if you are here, if you're looking at this region, and if you try to perturb this guy, which is, I don't even know what this is. Let's go to our easier region. So I think like this blue is a 0 and this red is 3. So for example, if you perturb this guy too much, then it will be close to here, which is a 3. So there's no guarantee that if you perturb this, that you will always get a 0, which goes the same for all these mixed neighborhood. Like if you perturb this, there's no guarantee that it'll retain its identity. This as well. And also interpolation is the same thing. Even if you interpolate like this guy and this guy, there's like two different digits between these two dots. So there's no guarantee that any sample or any point of the interpolation will retain its identity. So it's not guaranteed to work always because, as I said, it's not clearly, it is not always the case that your neighborhood is filled with the same ones or same sevens or same zeros. Like there are, like here, like 4, 5, 7. So it's not guaranteed to work. And this is actually, I've actually tried perturbing a trained autoencoder. So I took a trained autoencoder, which is trained on MNIST images for 50 epochs. I just manually did it. And I pick a actual nine, which you can think of as an X, is an X. This is an X. And it's a reconstruction of the X. So there's got to be like some Z between this X, right? So taking this Z, I've actually tried perturbing it and see what kind of new nines I get, right? So I take this and I perturb it a little bit so we get like Z like prime or Z double prime or Z or oops, or Z triple prime, right? With a small amount of noise, which is uh Gaussian distribution with 0 mean and 0.5 for the standard deviation. So you just add this small amount of noise to Z, and then you get Z prime, Z double prime, and Z triple prime. And then you put it through the decoder to get X. Well, if this is X prime, then I'm sorry, yeah. Well, this is a, okay, we can just think of this as an X reconstruction. It's reconstruction, X original, and we can call this as X prime, X double prime, and X triple prime, right? So this is what, so these are those X prime, X double prime, and X triple prime. So after a slight addition of small amount of noise, you get to see that actually they still retain their identity pretty well. So this is a true reconstruction, and these are the perturbed reconstruction, and they are more or less like looking pretty much the same, except for this part, which is a little bit grayer than before. Like this is there's a clear line here, but there's like a slight grayed blurred area. But other than that, you cannot really distinguish if this and this, which is like better reconstruction of the true original. So small amount of noise. Like if you're like scared that you might like change its identity, you only add like very small amount of noise, then you won't get a pretty like a truly new sample. So let's add a little bit more stronger noise. Like we perturb the Z a little bit further away from its original place. Then you get to see a new style. Like not truly new style because they're like circle here and they're the angle of the line is pretty much the same, but still like even here, like you see there uh the circle is not complete. There's like a bit of a cutoff. So like here. So you can see and also there's a little bit of like dent here. So like adding more noise will get you to a bit of a new style, but compared to the actual generative, sorry, actual new like a lot of different nines, these are pretty much the same. So these are like X1, X2, X3, so different samples. It's a different sample from the original space, and these are the perturbed samples, and you can see that none of the six samples resemble any of the new, like truly new styles. So using autoencoder, you won't really generate new samples. You need a new way to actually truly generate a new sample. So that's where variational autoencoder comes in. By the way, I need to mute everybody. All right. So far, so good. So we move on to the variational inference. So as I said, variational autoencoder is our main topic today, but variational autoencoder heavily relies on the concept of VI, variational inference, which is a very well-known technique or well-known like framework, for example, used in a lot of different places in machine learning and statistical, like machine learning and statistical theory and whatnot. So we'll take a look at this. So everything about variational inference, it's the objective is to infer a posterior distribution. So posterior distribution, if you are familiar with Bayesian principles, um, so there's hidden variable z and so there's z and x. So I'm going to use that. So for example, the posterior distribution would be p given z, p z given x. And if we're using Bayesian principle, then there's px given z, which is the likelihood, and then there's pz, which is the prior, and then there's px, which is your evidence, and we can rewrite it as px given z, pz, and um, p, sorry, over z, px comma z dz, which is joint distribution, or you can even go further, p x given z, p z, integration over z, p x given z, p z, and dz. So they're all yeah, I don't like the z a lot, right? Yeah. Okay. Anyway, so they're all the same. This all the same. And especially we should take focus onto this part, which is you have the same px, the likely and prior on the top on the numerator part, and also you have the same p, the likelihood and the prior on the denominator. It's just that this part is integration, right? So in this Bayesian framework, we call this the posterior distribution, this posterior distribution. With this, we call this likelihood, and we call this prior, and we call this entire thing on evidence. So what we have is we have access. We're going to assume that we have access to the likelihood and the prior, and somehow we want to get this, the posterior, calculated or inferred. All we have access to is these two. And what we want is we want to be able to calculate the posterior. So that's the posterior distribution inference problem, and VI is one way to solve this. There's a lot of different ways to solve the posterior distribution inference problem, but VI is one way to do it. Oh, there's a question. Is it possible to train VAE model with the images that it generated? For instance, if we have an image of dog and let VAE generate variations of this image of a dog, can we train the model with newly generated variation of images of dog as the input? Yeah, you can do it, but that would be just training your model based on its own creation, which will probably get you to a very like weird local minima. So your model will only probably degrade its performance because you are so all the generative models are trained to approximate a true distribution of a true data. For example, let's go to So we have a true population of like all the, let's just assume that we're dealing with all the MNIST images. So it's a 784 dimensional space where there are a lot of different elements, and this is like there are like ones here, there's like twos here, there's threes here, there's fours here, and fives here, like something like this. And then there will be like some distribution over like this is a three, and then one, and five, and four. Like there will be distributions of data, right? And what you want in all the generative model, like GANs or VAEs or autoregressive models, whatever, they're all trained to approximate this true distribution, this like like ups and downs, the density the probability density, right? And if you can do a good job, then your approximated VAE will learn its latent space that approximates like 3, 1, and maybe not maybe 5 is a little bit weak, and maybe like 2 it learned really well, and 4 like this. And then there are some like errors like here, there's error like here, like this, right? And what you're trying to do is you're going to sample a bunch of different new samples, like x prime, x prime, x triple prime, x. Let's no, this is a bad notation, like x x1, x2, x3, x4, x5, and x6. And if you really sample really a lot, then if you sample like, I don't know, like trillions of samples, then your samples will approximate your true latent distribution, which is this, right? All you can do is sample from your learned latent space, and then if you sample infinite amount of samples, then your samples will consist or approximate the VAE's learned latent space. Then if you train your VAE based on its infinite samples, all you can do is just strengthen your assumption or your bias. The true distribution is like this, and VAE is only approximating by learning, by training your neural networks backpropagation. And if you further train your VAE based on its own generation, then you're only strengthening or amplifying what it's learned, which is not the true distribution, which is approximate distribution. So you're probably just going to strengthen your bias, the model bias anyway. Do you see what I'm saying? The only way to improve the performance of your generative model is get more data from your true distribution, not your own learned distribution. Probably, yeah. I wouldn't say that your model will always overfit, because it's a strong statement, but I would say more likely than not. All right. Good? Okay, cool. All right, back to the VI. So typically, the example that I like to use in posterior distribution inference problem is a news article. So for example, let's say that we have a bunch of news articles. So this is document 1, this is document 2, this is document 3, right? There are a lot of news documents, and each document will have a category, assumed like topic. It could be like sports, politics, international relations, celebrity, science, society, whatnot, right? So there are different categories. And we're going to assume that when the journalist was writing a document, writing a news article, they had a certain distribution of topics in their mind. For example, a journalist could say, okay, this article is going to be about 30% celebrity, 40% society, and 20% international relations, something like that. Then based on that assumption, the journalist will write a article, which is the article that we will see, right? So sometimes this will be 20% celebrity and like 30% uh, society and 50% science, something like this, right? And this will have a different distribution. This will have different distribution, and all individual documents, we are going to assume that it has a distribution of topics, but we don't know which. I'm sorry about the noise. So, but we don't know the exact distribution of topics because we don't have access to the topics. Only the journalist, when he or she was writing the article, they know the distribution, but as a reader of the news articles, we only get to see the actual documents, which is X. So we're going to call the document, X, and the distribution of topics, the topic identity, the Z. So the shaded ones, the shaded variable is the variable that we can observe, which are the news articles. And Z, the topics, are the unobservable news articles. I'm sorry, unobservable topics. And this N is the number of samples we have. So there are like D1, D2, D3, all the way to DN. So there are a lot of different samples. And so this is something we call a plate notation. And you can see that the arrow here, which means that the Z will determine what we see, the X. So depends on X, relies on Z when for this generative process, right? So the problem is when we read the news articles, how can we infer the topic, the Z, which is again this. So we have access to X here, but we want to infer Z based on the X. So this is PZ even X, and this is the posterior distribution inference problem, right? And there are certain assumptions when we're dealing with this kind of problem. So we erase all this. We're going to assume that we do know PX given Z and PZ. So we do know how, given a topic, we know how to generate a news article. For example, if we say that I'm going to write a science article, for example, the topic is science, then we know that the distribution of tokens will be like 1%, let's see, like physics, and 2% Newton, and 0.5% Einstein, and something like that, basically. Like, and if we're talking about celebrity or politics, then it's like 1% Trump, 2% Biden, 3% Israel, 4% like Hezbollah, something like that. You know, so when the topic is determined, then we know the distribution of tokens. So that's what we're going to assume that we know, which is the likelihood. And we also know the prior, which is the usual topic distribution. Like in all the world's news articles, it's basically just usually the topic is distributed, such as like most of the time people write 20% 20% politics, 20% of the time politics, 30% of the time society, 10% of the time public relations. So that would be the prior, like what journalists usually write, the topic that the journalists usually choose. So we're going to assume that we have access to the likelihood and the prior, and then this, but we don't know how to calculate this. So we're going to infer. So that's the posterior distribution problem. Yeah. Any questions so far? So knowing the setup is important, and the objective, the large picture, which is we do know the likelihood. We're going to assume that we do know the prior, and what we want to do is we want to be able to calculate posterior distribution. So back to our news article, we can, for example, we can simply assume that the PZ, PX given Z is multinomial distribution, because when the topic is given, then there are just different tokens that we can choose from, like from A to Z, from like Obama, Trump, Biden, USA, South Korea, GPU, like there are different, like a lot of different vocabulary, right? So there is a multinomial distribution over the vocabulary when the topic is chosen. That will be this guy. And among the topics, let's say there are like 5 topics. There's celebrity, society, science, international relations, and politics. There are 5 topics. Then this PZ will be simply just a 5-dimensional multinomial distribution again. So we do have multinomial distribution here, and all we need to calculate is this guy. All right. So hopefully, some might ask, like, why can't we just calculate this based on this Bayesian principle? Because we know this, we know this, we know this, we know this. All we need to do is just integrate, and we're done. So sometimes that is true. For example, if Z is a discrete variable, not a continuous variable, if Z is a discrete variable, and there are only like two classes, for example, there are only 2 topics in our news article example, then all we need to do is just sum over Z, which can have only 2 values, and it's just for loop over 2 items, right? So then we can do it. But most of the times, when the Z is continuous, then it becomes an integral. Or if the Z's identity, or even when Z is a discrete variable, if the values you can take is like there are like 1,000 topics or like 100,000 topics, or if we're dealing with like tokens in NLP, there could be like million different tokens, then the for loop again it becomes intractable. So usually dealing with a summation over possible values is intractable. So that is why P z given x is also intractable. So that is of course you can take like you can for example like sample from this using like Monte Carlo simulation. We can sample and then try to calculate this based on your sampling, but that's another topic that we can talk about. But today we're not going to talk about sampling, but we're going to talk about VI, variational inference. Intractable means just it's hard to calculate. Z, for example, when Z is a continuous variable, how are you going to integrate over the entire space of Z? So, this is the same thing. Given data X and a hidden variable Z, how can we calculate this posterior distribution? And as I said, the topic Z could be a topic and X could be a news article in my example. But in our autoencoder, X can be MNIST images and Z can be the latent variables. So there's encoder, Z, and decoder, right? So in this case, this is our latent variable, and this here is our observable variable, which is the image itself. So in this case, given an image, how can we infer its latent variable or the compressed latent variable Z? That would be the question for the autoencoder, right? So we start with this, and because this is often combinatorially large, or even infinite. For example, if we're talking about continuous variable, this could be infinitely large. And this integration is the problem. So what we are going to do is, instead of trying to somehow do the integration analytically using like solving like derivation and whatnot, or rather trying to sample from this distribution and somehow just do away with the Monte Carlo simulation, what we're going to do, instead of all that different techniques, we're going to assume that we're going to assume that this function, the final product, final objective that we're interested in, can be approximated with a known function Q. When we say known function, which usually means we're going to assume that this guy is a Gaussian distribution. So Q is a Gaussian distribution. So Q, instead of, for example, we do know this, and we know this, but we don't know this. So we don't know what kind of shape this PZ given X will take. But if we can assume that it'll take a bell-shaped curve, then it makes sense to approximate PZ given X with a Gaussian distribution, QZ, right? So QZ will be actual Gaussian distribution, will be a real Gaussian distribution with mean, with mean and standard deviation, right? Standard deviation. So we're going to somehow tune these two parameters of Q so that Q and PZ given X will be as similar as possible. So that's what we're going to do. So first of all, we're going to assume that this is bell-shaped, or more or less bell. If it's like multimodal, then this is not bell-shaped, because QZ has just one mode. It's a unimodal distribution. So if PZ given X is like multimodal, then that's not a approximating PZ given X with the QZ is not a good idea. But that's the best we can do so far. We're just going to assume that using a Gaussian distribution, we can somehow approximate the true PZ given X, the true posterior distribution, which is our objective. And how are we going to do it? We're going to tune these two parameters of Q so that they are as similar as possible. So how do we, oops, why are we here? Yeah, so that's our main idea. All right. So when we say that we want to make two distributions as similar as possible, we usually turn to a KL divergence, Kullback-Leibler divergence, right? So here, I mean, usually what we do with Kullback-Leibler divergence is there's DKL and there's P and Q. So when our target distribution, the one that we want to approximate is P, and the thing that we're going to use to approximate is Q, then usually when we're using KL divergence, the P goes to the left side and Q goes on the right side. But in variational inference, the places are switched. The one that we want to approximate goes to P on the right side, and the thing that we're going to use to approximate goes on the left side. So it's a QP, so it's a reverse KL. So variational inference uses reverse KL. If you use PQ, then it's becomes something called expectation propagation, which is something else, something different from VI, variational inference. So in today's material, we're going to stick to this reverse KL formulation. So the KL divergence is a divergence. It's not a distance. It's not commutative. For example, if you look at this formulation here, if you switch places between P and Q, then this will be P, this will be P, this will be Q. So they're not the same. So switching places between Q and P gives you different results. So KL divergence is not a distance. It's not commutative. It's a divergence, and its values can be can go as low as 0. So when KL divergence is 0, that means these two distributions are exactly the same. Anything that is non-negative, so KL divergence cannot be negative. So it's either 0 or positive, right? So positive value means that these two distributions are different. And only when these two distributions are identical, then your KL divergence will be 0. Right. So we want to somehow tune Q or optimize Q so that KL divergence becomes 0. That's our objective, right? So far, so good. And throughout the material, we're going to assume that Z is a discrete variable. So instead of using integration, we're going to use summation over here. Right. So we expand terms and move the terms around, but it's not very hard. You can just follow one step at a time. So this is our definition of a cubic Leibler, the KL divergence. And what we do here is we take PX here out to here, right? So now this becomes a joint distribution. And since PX was on, so this can be rewritten as X comma Z PX, right? So PX goes over to on this side. And then here, what happens here is you take this guy and put it in front of here. So you have this guy, right? And also the numerator comes here and the denominator comes here. So far so good, right? So far so good. And what we do, if you look at this part, what happens is this is actually what? This thing is expectation over Z distribution with log PX inside, right? Because this is a probability distribution and you're summing over it. So basically that's just expectation, right? So this is exactly the same thing. And since the inside has nothing to do with Z, like inside is only about X, right? So inside, this has nothing to do with the Z, which is we're averaging over. So we can just simply drop this and have this instead. And this part is exactly the same, right? And for the last part here, we just simply do expectation again. We convert this into expectation, and the inside is exactly the same. So we started from the definition of KL divergence, and we arrived here. No biggie, no biggie, right? Question. For clarification, P in DKL QP is P Z given X, right? Yep, exactly. You can see it here. So Q is QZ, P is PZ given X. All right, I'm gonna move on. So we take this guy and copy paste it here. And what we do now is we take this guy and move it over this side so that log PX will be on the one side and these two will be on the other side. So this is it. So log PX on the one side and these two on the other side. So the reason that we do it is, yeah, okay. So I think I need to go one more page, right? So once we've moved the terms over to this side, then we get this. So log PX equals this guy, KL divergence, plus something called elbow or evidence lower bound. So including the negative sign here, including the minus sign, this entire thing is called evidence lower bound, elbow. And if you like study machine learning enough, then you probably have seen this term elbow in some papers, like they call like maximizing elbow, minimizing elbow, and elbow, right? So this is called elbow, including the minus sign. Don't forget about the minus sign. So we can rewrite this as log px equals dkl plus elbow, right? And maximizing elbow leads to minimizing DKL. So remember that what we really wanted to do in the beginning was to make this as small as possible, possibly zero, because we want to have the Q approximate P as much as possible. And when that happens, your DKL will be as small as possible. So what we're really after is minimizing this. But instead of doing that, what we can do is actually maximize this instead. And that'll actually lead to minimization of DKL. Why? Why is that? Why is that? As says here, because log px is fixed. Log px, or if you look at just the px, log is just like a monotonic increasing operator. Px is your data distribution. If you're thinking about MNIST images, then px is just a distribution of all the MNIST images in the world. So your px is fixed. Your data distribution doesn't change whatever you do with z or like p sigma x. It doesn't have anything to do with that. Px is just something that exists in the world, and it is fixed. So that is why these two have a bit of a power struggle. If you increase elbow, then DKL will decrease, and vice versa. If you decrease elbow, then DKL will increase. But that's not what we're after. We are after this being minimized. So you can instead increase elbow so that this will be automatically decreased. So that's the whole idea behind variational inference. So what we've done is we have converted an inference problem. So why the inference problem, this is not an inference when we say like ChatGPT inference. That is not what we're talking about. The inference problem is the Bayesian principle, using Bayesian like this. Oops. So you starting from here, likelihood and prior and evidence, deriving the posterior distribution is what we call an inference. We're trying to infer posterior distribution from the likelihood and the prior. So that's what we call a inference problem. But that is really hard because it entails an integration over the entire evidence, entire data distribution, which is intractable usually. So inference is hard. But what we've done instead is let's just increase elbow so that your DKL will be minimized. And so following, decreasing the DKL will mean that your Q is similar to P. So what we've done is we're going to optimize, or we're going to maximize elbow, which is an optimization problem. So what we can do is simply just try to maximize this value using gradient descent. Like we can use any of the optimization technique that we've learned so far to maximize this value, and that is way easier than inference problem. Optimization is easier than inference. So that is why we are using variational inference. So, and when we're optimizing, when we're maximizing this value, what we're actually doing is trying to tune this parameter Q, right? Tune this parameter Q, or more specifically, the mu and sigma of the Gaussian distribution that we're going to use, so that this value will be maximized. And thankfully, you can turn this into Px given z and Pz, right? Which are the values that we already have knowledge of. We do know, as I said, we're going to assume that we know the likelihood and we know the prior. So now we know all the values inside. So we can easily optimize. Problem, question. So if you keep updating or optimizing, we will eventually get KL value close to the distribution of the value sample. I mean, the KL value will be close to 0 because DKL is divergence. So we want to make it as small as possible. So KL, if your KL value is small enough, then it means that your Q is now similar to P. And then when your Q is similar to P, we can simply sample from the Q, or I'm going to call it Q star, which is an ideal Q. So if we sample from Q, we can sample like Z1, Z2, Z3, yada, 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 right? these values will be similar from what we can actually sample from PZ given X. Z1, Z2, Z3. So we don't know, we don't have access to this, but now we have access to this, and if we can simply sample from it because this is normal distribution, then the samples from this Q star Z and sample from this PZ given X will be more or less the same. That's the whole idea. Because what we had in mind is if I read a newspaper, I want to be able to infer its hidden topic distribution, like 20% science, 30% celebrity. I want to be able to access that infer that information. Since we have Q star Z, now we have this instead. All right. So hopefully that it makes clear. I don't know why you're asking. It's kind of like MLE. I guess you don't have a clear understanding. I said the value of DKL is either 0 or positive. All right. Any other question? If not, let's move on then. It's just a side note. So sometimes if you look at this part, if you actually look at just this part, this is what? This is an entropy, right? So sometimes the evidence law over elbow is called information entropy because you can convert this into an entropy term like here, and the PZX goes here, right? So sometimes people call this variational free energy. Sorry. This is the entropy. Sorry about that. Sometimes people call elbow a variational free energy. It's some like concept borrowed from thermodynamics, but it's just a side note. Yeah. We're gonna stick to this term elbow. Right, now we move on to variational autoencoder. So keep in mind what variational inference was for. Variational inference is all about inferring PZ given X from the PZ given X from PX given Z, PZ, PX. This, we want to access this, and there are a lot of different ways to do it, but one way to do it is approximate this PZ given X, the posterior distribution, with Q, which is a controllable, manageable function, and where you're going to use KL divergence to minimize the gap between Q and PZ given X. And in deriving throughout the whole derivation part, we've figured out that log px is fixed, so we can just instead maximize this so as to minimize this, which was our true objective. So that's the whole setup. We're going to maximize elbow instead of minimizing DKL. All right, moving on to VAE then. So VAE, the objective is actually pretty simple. If you just simply look at the loss function, then VAE is nothing but just an extension of autoencoder. Just like denoising autoencoder or sparse autoencoder, variational autoencoder is just another extension of autoencoder. And yeah, we all know this. So instead of having a vanilla autoencoder, there's one more condition, which is that the latent distribution Z, latent variable Z, we want the Z to follow a certain distribution. That is the only added condition. The other is exactly the same. You want to compress and decompress, and you want the X prime to look exactly like X prime to look exactly like X, right? The only addition to the vanilla autoencoder is that we want the latent space to follow a certain distribution, which is usually a Gaussian distribution. So if you remember the scatter plot here, this autoencoder, latent space, doesn't follow any distribution. There's no guarantee that this will follow a Gaussian distribution or beta distribution or like any other distribution. There's no guarantee. It'll just be shaped in a way that maximizes your reconstruction performance, and that's it, because that was the only condition, that was the only guide to shaping the latent space, which is reconstruction loss. But in VAE, we want an added one more condition, which is that we now want the latent space to look like a Gaussian distribution, for example. But it could be any other distribution, but in VAE, we typically use Gaussian distribution. So how do we do this? So let's turn that loss function or encoder and decoder into a little bit more of like a probabilistic terminology. So your encoding will be we're going to call our encoder Q, and we're going to call our decoder P, and each of them have controllable variable, like they're controlled by their own parameters, theta and phi. So we can, if we turn back to our original autoencoder, this Q theta is what? It's just an FWX plus B. And these two will be the thetas. And obviously, P phi goes the same. FW, well, I'm going to call this W1B1, W2X plus B2. And now W2 and B2 is the phi, right? And so you understand this, like, because Q, the encoder, will receive a specific X sample and then generate Z, which is the output, which is the output of Z, which is output of the encoder, which is the latent variable. And the encoder and the decoder will receive the Z, the latent variable, and then reconstruct the X. So you can understand the notations here. And what we want is, we said that we need one more condition, which is that we want the latent space to look like a Gaussian distribution. So we can add a KL divergence as an added loss function. So the loss function is typically what? It's an MSE. So plus this guy, KL. This is our VAE loss function. VAE loss function is this part is original autoencoder, which is a reconstruction loss. This is the new regularization, just like what we did in sparse autoencoder. We had a sparsity inducing regularization term, such as like we also use KL divergence there, and also L1 regularization, right? And so it's just like that. We have one more regularization term, which is to regularize the shape of the latent space. So we use KL divergence between the output of your encoder and a prior, which is usually a standard Gaussian distribution, the Z distribution. Normal Gaussian distribution with zero mean and standard deviation of 1. That is what we call typically use as a prior distribution. So if we add this term in addition to the autoencoder, the vanilla autoencoder reconstruction term, then we are going to maximize the reconstruction performance while we guide the latent space to look like a Gaussian distribution. So that is it. In terms of loss function, this is your VAE, right? So this allows us, what's good? What's good about having your latent space shaped like a Gaussian distribution? Why do we want to do it? The reason that we want to do it is we want to be able to sample from this latent distribution and create a new sample, right? So before, with a vanilla autoencoder, this being your X, this being your X, this being your Z, this being your X prime. When we wanted to generate a new sample, what we could do is just take a Z and perturb it, right? Slightly perturb it so that hopefully we can get a similar looking sample that is slightly different, right? So that was the best way that what we could do with vanilla AE. But when we have a guarantee that your latent space looks like a Gaussian distribution, then we can just sample from the Gaussian distribution, and they will all look like a realistic sample because your latent space looks like a Gaussian distribution. You see what I mean, right? Before, there was no guarantee that your latent space would look like any distribution. It's just random distribution, right? It's just random dots, like 1s here, 2s here, 3s here, 4s here. There's no guarantee that it'll look like any distribution. So if you sample from your latent space, then there's no guarantee what you're going to generate. It could look like a realistic one, but it could look like a completely non-digit image. But if you can enforce your latent space to look like a Gaussian, then you can sample. So there's a nice picture, right? Yeah. So yeah, I should have actually turned to this picture. So this is the vanilla AE latent space. This is a variational autoencoder latent space, and you can see this is way more like a spherical shape, like a bell curve. So if you sample from this space, like anywhere, like probably like there will be a lot more samples here because it's a bell shape, and then less samples here, then way less sample here, and way less sample here, right? So if you sample from this Gaussian distribution, then it's more likely than not you will get a like a realistic digit image. But if you sample from this space, then there's a chance that you will sample from this region or this region or this region or this region, which are all out of distribution, right? If you sample from this region, this will look nothing like a digit image, nor here, nor here, nor here. You'll have to be very careful to stay within this weird shaped latent space, which is not easy because we don't have the like a mathematical equation to model this latent shape. But here we can just simply use Gaussian distribution with a proper mu and sigma. Then we can always get a new realistic sample out of this. So that is the good thing about VAE. So far, so good. Question: we want the distribution P as similar to Q as possible. No, that's actually the other way around. We want the Q to look like P is equal to X. So I suppose that we should calculate KL, not PQ, but KL QP. You have it the other way around. So PZ, sorry. So PZ given X is the one thing that we're after, and QZ is what we're going to use to approximate our objective. And in variational inference, we use DKL QP. Not the other way, not the other way around, DKL. Not this one. We're going to use this one, which is reverse KL. All right. Does that answer your question? Question: if we enforce the latent space in VAE model to follow normal distribution, is there anything that we lose? I mean, based on the image we have here, AE seems to have a proper latent space representation, right? That's a good question. That we have something to lose. I'm not sure what you mean by the second sentence, but in the first question, is there anything to lose by having, like, enforcing the latent space to look like a variational inference? Sorry, enforcing the latent space to look like a Gaussian distribution. Are we losing something? Obviously, there's a chance that your reconstruction performance will get a little bit of like a hit. Your reconstruction performance might decrease a little because for example, if the only objective that we enforce on our autoencoder is reconstruction loss, then this is what we get. And probably this is the optimal latent space to maximize your reconstruction performance, as opposed to having to enforce a latent space that looks like a Gaussian distribution. Because this here, you can only focus on getting the best reconstruction as possible. But here you need to care about two things, which is getting the reconstruction as good as possible, but also having your latent space shaped like the Gaussian distribution. So you need to care about two things. So probably this one's reconstruction performance will be slightly worse than this one's reconstruction performance. So there's always a trade-off. But if you increase the latent size of your latent distribution, if you increase it from like 4 to 8 or 16 or like 32, then probably you can make up for that. So if you use a larger latent space, then enforcing your latent space to look like a Gaussian distribution might have like a reduced impact to the reconstruction performance. But if you want to stick to like the 4-dimensional, if you're doing like a head-to-head comparison between AE versus VAE using the same size latent space, then AE will most likely give you a better reconstruction performance. But then what we're after is a generative model. So VAE and AE serves a different purpose. All right. So that was it, but there's a deeper meaning into what VAE is actually doing. In addition to having, you can interpret VAE as just, oh, there's just like a reconstruct. So there's, do I have it here? Yeah. So in terms of a loss function, VAE is just simply reconstruction loss and KL divergence as a regularizer, and that's it. So reconstruction loss here and regularization term to force the Z to follow a Gaussian distribution. So in terms of loss function, that's it. So we just add one more regularizer on top of your MSE, and that's it. But there's a deeper meaning into it if we actually look into the mathematical equation a little bit harder. So this one, you might wonder why this is an MSE, but let's just take a look at it. So here, what's happening is P is our decoder, and it gets our latent variable z and then reconstructs the original image. So p is what p will give you x prime. And the z comes from your where? Comes from your encoder. So encoder will accept x and give you z out, right? So from your encoder, we can get z, and then we plug that into the decoder, then we'll get x prime out. We want to maximize the x prime's log likelihood, which is the same thing as MSE, right? So this part is a MSE part, or a log likelihood part, and this is the regularization part. Yeah. Yeah, in autoencoder, yeah, as I said, negative log likelihood is the reconstruction, is the MSE function. So what we do, so this is our loss function, but let's go back to the variational inference and see what we're doing. So what we're doing is we want to infer the PZ given X posterior distribution. In terms of autoencoder, what we want to do is we want to infer the latent variable Z given the image X, right? So that's the posterior distribution. And if you compare this guy, which is our original VI. So this was QZ, and this was P Z given X, right? So this is the KL divergence definition. And let's just, in our example, Q is the encoder, P is the decoder, and the Z will depend on X because our encoder will receive X, and then generate Z, right? So our encoder depends on X, so we're going to use Q as a Z given X now. It's no longer a QZ, it's a Q Z given X, and the rest is the same. So if you compare this guy with this guy, the only difference is that Q, Q, and Q, Q, and that's it. The other is the same. It's the same likelihood here, and same the joint distribution here. Well, I mean, it went into here, like here, but the joint distribution is the same, and the only difference is that Q is now a conditional distribution. So it's still the same, like, right? Still the same. And you can see that Q is now, well, actually Q here, there's like a lambda here, which is our control variable, which is that we assume that Q follows a Gaussian distribution, right? How Q, so forget about the encoder and decoder, but what we're doing is we're going back to the variational inference, and I said that usually we set the Q to follow, we set Q to be a manageable function, which is a Gaussian distribution. So there are two variables or two parameters to tune so that as to minimize KL, right? Here it's the same thing. We're going to assume that Q Z given X is a Gaussian distribution. So there's mu and sigma, which is lambda, same thing. Q and we have a mu and sigma to control this guy so as to minimize this guy, or rather actually maximizing the elbow actually. Right. So yeah, what we want to do is we want to learn an encoder, Q star, which can minimize this guy, the DKL. So we want to Q this guy to be something with some value, mu and sigma, that minimizes our KL divergence. And so we move the terms around. We set this guy on one side and this guy on one side. So originally, we set this guy, we pass this guy to here, and we have one log px on the one side and the other on the other side, and minus this, negative this was the elbow term, right? So this was the elbow term, negative, you can see the negative here. Same thing, the negative this will be our new elbow with the conditional Q. So here, the new elbow, right? So if you put negative here, this will be plus, this will be positive, so positive comes here, and negative comes here. So our new elbow. So instead of minimizing this, we're going to maximize the new elbow, right? And so how do we maximize it? By tuning this mu and sigma. Right. Yeah, this is the same thing. It's just that these are just the new elbow terms, right? And here you can see that this new elbow term, if we look at the autoencoder part, if we try to make it into more look like an autoencoder, X, this Q becomes this guy, and P becomes this guy, and Q becomes this guy. So you can see that this has changed. This has changed, right? This has changed. Why did it change? Why did it change? Because we put, so if you look at this guy, this will be px given, oops, sorry. This is p, yeah, if you, for example, like if you have pz here, if you divide it into px given z, pz, then this pz goes to here, and you're left with px given z here, right? I'm not going too fast, right? This can be rewritten as px given z, pz. Let me just write it in a pen. So this can be written as px given z, pz, and this pz went to this side, and if you have pz on this side, this becomes KL divergence, right? And you're left with the likelihood, which is here, here, and Q is just the same Q, right? It's just the same Q. Well, I mean, this becomes a K. They didn't expand the Q to be like this, like this, because this automatically becomes a KL. So no like difficulty here, right? It's just a manipulation of terms. So let me just erase all this. Right. So as I said, our encoder depends on specific sample mnist digit image, a specific mnist digit image, and then based on that, it can generate Z, and that's why we write it like this, right? So if you look at the new elbow term here, then you can see that, well, yeah, we call it parameterized elbow term, but this is just like a manipulation of the concept. So far, we've only stuck to like a true variational inference derivation, but now you can see that the lambda has become a theta, and now p has a phi, which is why, which is because we're going back to the autoencoder notation, where the autoencoder had controllable parameters, which is theta for the encoder and phi for the decoder. So we're just plugging them back in. So what's happening here is, in the original variational inference derivation or framework, Q was the only thing that we could control. Specifically Q's mu and sigma was the only thing that we could control so as to maximize the elbow. But in our autoencoder, there are two parameter sets, which is the theta and phi. So we now can control two parameters to maximize the elbow, which is a little bit different from the original elbow, right? So to keep that in mind, we have two controllable parameters, which is theta and phi, which is for the encoder, which is for the decoder, right? And we can control these two parameters to maximize the elbow. So that is the difference between this guy and this guy. And yeah, question is, does this formulation remind you of something, right? So what we did is we started from P, the posterior distribution inference problem. So we had access to the mnist image X, and we wanted to infer the latent variable Z. So that's the inference problem, and we derived the elbow. And this is the true elbow in terms of encoder and decoder parameters. And does this elbow remind you of something? And if you look at the loss function that we defined way over in the back, this was a loss function, right? This was MSE plus the KL regularization. If you keep that in mind, then our elbow term is exactly like the loss term. It's just that elbow should be maximized and loss should be minimized. So there's like negative and plus, which is here. So it's the same thing. It's just two sides of the coin. So elbow is actually just the loss function. So as I said, if you look at the VAE as just a simple extension of autoencoder, which is MSE plus a regularization term, then you can interpret it like that. That's no problem. But in the deeper meaning of that loss function is that what we're actually doing is maximizing the elbow. When we said, oh, I want to minimize the MSE while also minimizing the KL divergence so that I want to have the latent space shaped like a Gaussian. That's one way to think about it. But when you are doing it, what you were truly doing is you were maximizing the elbow term. That's the beauty of VAE, basically. It's that it looks like just a simple extension of autoencoder, but it's actually it can be also derived from the variational inference framework, and you can view the loss function as a elbow term. Well, I mean negative elbow, actually. All right, so far so good. All right, I'm gonna move on. Yep, VA elbow is the negative loss, and that's it. So the maximizing elbow is equivalent to minimizing the loss. And as I said, yeah, elbow can be maximized by both updating the encoder's parameter theta and decoder's parameter phi. So we have two controllable parameters, but in reality, what we do is we just maximize them both at the same time, like in an end-to-end manner. We update both parameters. So when we actually implement this VA in PyTorch, we update these two parameters, theta and phi, at the same time in an end-to-end fashion. Right, so training to VA. So that was the whole concept behind VA. And as I said, we need to care about one more thing when training VA. So how do you train your network? So this is our loss function, but this is all like, well, it's mathematical. We haven't actually written in code. So when we're writing this in code, there's something that we need to think about. So how do you train your network? So there's like a step-by-step thing, which is using a single example. So you can think of this as a true stochastic gradient descent, right? We push our sample into the encoder, and then we obtain. So let's go back to this. I need to make a bit of a drawing. So there's like you have bunch of x's. So this is our x space, and you have bunch of x1, x2, x3, x4. So you sample you sample a single xi, and then you plug it into your encoder, which is q theta x given z. Oh, sorry, this is the other way around. Z given xi. And in the original autoencoder here, your encoder directly gave you x from z, x from z, I'm sorry, x to z. But here, as I said, there's a bit of a, we're assuming that Q follows a Gaussian distribution. So here, what we do is, instead of Q giving you z directly, this is not what we're going to do. This is not what we're going to do. Instead, we let Q output two parameters, mu and sigma, right? So now encoder doesn't give you directly the x, directly the latent variable z, but instead it generates a mu and sigma, which is specific to this guy. We get mu and sigma, and then based on the mu and sigma, what we can sample. Well, I mean, I guess this is oops. We can, based on mu and sigma, which is a parameter for the Gaussian distribution, we can sample a new z. So we're going to call this a zi. And then based on zi, you plug this into your decoder, which is x given zi. And then your decoder will actually give you back the x prime, well, xi prime, right? So this is our whole formulation of variational autoencoder. So there's a bit of a change in this part. Instead of Q giving you Z directly, we let the Q generate mu and sigma, and then we sample from that the Zi. So might as well just write this as mu I and sigma I, because this is specific to this example here. Question, so Zi sample randomly, how do we backprop in that case? Exactly, that's the problem that we're going to address. That's a very nice question. How do we backprop? Because there are two parameters to fine-tune. There's parameter 1, decoders, and parameter 2, the encoder. So we need to optimize two parameters, but as you said, because there's a sampling phase here, your backprop signal will be cut off here. So this part is okay, because so far so good. This part is deterministic, right? So you can backprop. So actually, I forgot to write one more thing. So using this xi, we can have a loss function MSE between xi and xi prime, and there's also the second. I'm gonna write right here. Second loss, which is DKL between Q theta and PZ, which is, well, I'm gonna make it a little bit clearer. Just normal distribution, standard normal distribution. But note that this is a PZ prior, right? So there are two parameters to tune. And this part, MSC, so this part entails this guy, because xi prime comes from your decoder. So when you backprop your file will be updated, no problem. But when you want to go all the way to here so that you can also update your theta, but because of this sampling process, you cannot. This backprop signal will be cut off here. So that is what, yeah. Oh, that backdrop, yeah, yeah. So that is why we need something called reparametrization trick. So we're gonna forget all about this. We're gonna move on to to let's move on to yeah, this part. So I mean there are a lot of like laid out in detail description, but I pretty much summarized the gist of it, which can be summarized by just this one picture, one picture here. Like updating this, no problem. Updating this is problematic. And actually, there's one more thing. Actually, we should talk about this part. So this here, the Q theta follows a Gaussian distribution, using following this mu and sigma, right? So Q theta will give you mu and sigma, and that will be actually, let me rewrite it. Mu I, sigma I. So this will be your DKL, and this is exactly the same thing as Q theta output, right? So right here. And when these two, so pertains to the characteristic of the KL divergence between two Gaussian distributions. So KL divergence between two Gaussian distributions is analytically solvable. Analytically, you can write it out, the formulation. And especially when the other side is a standard Gaussian distribution, the zero mean and one standard deviation, it's extremely easy. It becomes like this. So KL divergence between one Gaussian distribution and another standard Gaussian distribution is basically this. And we want to minimize MSE and this guy, right? This guy. And note that these mu's and sigmas come from where? Come from the encoder. So this part is actually, this has nothing to do with the sampling because Q theta will give you mu and sigma, and you can just plug them in here and here and here, and you can just calculate this and then try to minimize this. So it has nothing to do with the sampling and all that. The only thing that sampling becomes a process is when you're calculating the MSE loss, because MSE loss will have to back propagate all the way back to here, and this becomes a problem. So this whole slide is talking about like that. Like we need to backprop, and then we can get this, which is the decoder's parameter. Getting this is easy because decoder is right before the loss function, but getting this becomes a problem. So this is our sampling process. So let's draw a Q theta here. I think it was a small q. Q theta here with mu, I'm sorry, z given xi. Well, let's forget about the xi here because mu doesn't have I here. So Q will give you mu and sigma, and then based on your mu and sigma, you can sample z, and then this will lead to the MSE function, the loss function. And this becomes a problem because this is a random variable. So you cannot backpropagate here, and eventually what we want is we want to backpropagate from the MSE to all the way to here and all the way to here so that you can update your theta. So this becomes a problem. But what you can do instead is when you're sampling from a Gaussian distribution, you can actually, so Z follows a Gaussian distribution of some mu and some sigma, right? But you can rewrite this as Z equals mu plus sigma times some small error, where the small error follows a certain Gaussian distribution, which is usually, not certain, but standard Gaussian distribution, sorry. So this can be rewritten as this, and now your randomness comes from a standard Gaussian distribution, and it can be written like this. Let me copy paste. See if I can copy paste this. Oh, I can. Nice. Uh, oh, nice. Okay. Right. Let's keep it right here. So this is what depicts this guy. It's the same thing. So your Z is deterministic. And oh, I forgot to draw Q here. So there's Q theta coming from here. And now you can see that your Z is deterministically, at least it doesn't depend on mu and sigma. Z will be deterministic, the randomness only resides in the epsilon part. So Z is now this, and the mu and sigma, the relationship between Z and mu and sigma, they're all deterministic. There's no like sampling or anything. So now you can backprop from your MSE all the way to here and all the way to here, no problem, because you have separated the randomness factor aside to this standard Gaussian distribution to the side. So the backprop chain is all deterministic. So far, so good, right? This is what we call a reparametrization trick. And it's real widely used in a lot of different ML, like deep learning like studies and deep learning techniques, especially when you're dealing with Bayesian neural networks and all that. Because there's like when you're doing sampling, there's always this back propagation problem. And you can set, as long as you're using Gaussian distribution to sample, you can set aside the randomness into one part, and then you can suddenly now backprop through the whole chain. So that's the beauty of reparametrization trick. So reparametrization trick, randomness is removed from the backprop path. So now in the big picture here, this is the whole flow where you have input sample going into the encoder, which is controlled by the parameter theta. It'll give you a mu and sigma. And then based on mu, sigma, and epsilon, you will get Z out. And then this Z will be plugged into your decoder, which is controlled by your phi parameter. It'll give you a reconstruction. And based on your X and X reconstruction, you can get your MSE. And as I said, KL divergence is directly calculatable like this, like this. It only depends on mu and sigma, right? So that is that's what this picture is saying. It only depends on mu and sigma. So KL. So your loss function, your loss function consists of MSE and KL divergence. That's it. This is the whole big picture. Right, and I think yeah, I have a nice like a visualization for. Let me show you guys this. Can I? Okay, I can't. So this is when you actually train your VAE, this is what happens in the latent space. Yeah. So you can see that different numbers, they all like taken like are located in their respective neighborhood, and more or less the entire thing kind of follows a spherical shape. It's not exactly like a beautiful like beautiful spherical like Gaussian distribution, but more or less this is what happens in the latent space as you train. And what you can do is this is a nice like a picture of what really happens when as you train your variational autoencoder. And I want to can I control this? Okay, I cannot. Yeah, you just saw what happened, right? What happened is it was a pure noise in the beginning, but now as you train with more, as you go like one epoch, two epoch, three epoch, they become pretty much clear. Like the ones are being like they look like one and nine, 7, 9, and 0. And what's happening here is actually the author is what he or she is doing is let me draw something. So you can imagine there's a line here. So there's x-axis and y-axis. And the author used two-dimensional latent space. So the z is a two-dimensional variable, and what they're doing is basically interpolating between -3 and 3 on one axis and another -3 and 3 on the other axis. So there's like z here. So there's z here, z here, z here, z here, which is like -3. So the coordinate will be like -3 by 3, your z variable. And here it will be the coordinate will be 3 by 3, 3 by 3, and so on and so forth. You can see what's happening here. And then you're interpolating between these different grids or different coordinates. And so that becomes like Z1, Z1 here, Z2, Z3, Z4, Z5, Z6, Z7, Z8, Z9, something like that, basically. And they are plugging those Z's into the decoder and see what's happening on the outside as you train your VAE. And you can see that these axes have a pretty like nice semantic to it, because you can see here as you move along this axis, one is being a little bit less slanted. This is a little bit like there's like a bit of a slantedness here, but now this becomes upright. So this angle is kind of like a slanting angle, but not so much here, because you can see like this is 0, but now as you move on to here, you can see it's gradually changing towards 9. It's gradually changing towards 7 and 1. So it's a very nice depiction of what your latent space is actually capturing in its different coordinates and different axes. All right, so back to the screen. So those were the visualization. And yeah, just the conclusion. So VA is an elegant solution for approximating PZ given X. Well, actually VI. So variational inference is one of the solutions to approximating your posterior distribution. And as I said, VAE can be seen just as an extension to AE, but in reality, when you say that you're like optimizing your loss function, you're actually maximizing your elbow turn. And there's are some further extension to the VA, such as like normalizing flow and beta VA, TCVA, and whatnot. If you're interested, you can take a look at it. Normalizing flow, this is worth mentioning. So when you look at the variational autoencoder, there's like a space of X's, and then there's a space of Z, which is Gaussian, which follows a certain Gaussian distribution. Well, let's try Gaussian distribution, and there's a space of X prime, the reconstructed loss. And if you, for example, there's a certain disconnect between the input and output space. So if you look at this part, this is controlled by this process controlled by your Q theta, this process controlled by your P phi. And they are disconnected. The parameters of Q and parameters, the P, the decoder. So theta and phi, they don't have anything sharing. So what can happen is if you have a certain like the MNIST sample, like certain sample from the X space, and then you map it to a certain space in Z, and then which is done by Q theta, and then you map it back to your reconstructed space X prime, which is controlled by P phi. There's no guarantee that there is a one-to-one correspondence between this guy and this guy, because these two processes are operated or managed by two completely different set of parameters, theta and phi. So there's no guarantee that this guy and this guy have a one-to-one correspondence. Then like you cannot go back and see if this will be exactly the same thing. So that some researchers thought that was a limitation to VAE. So they actually came up with something called normalizing flow. So instead of using Q theta and P phi, what they did is they used a invertible function. So there's F here and there's F inverse here, so that you can guarantee that these two will always have a one-to-one correspondence relationship between the two. So as long as you use invertible function, like here and here, then there's like a guarantee that your input and output space will have a one-to-one correspondence. So that's what normalizing flow is about. So if you're interested, you can also study this, or these are extensions of VA so as to like enforce certain semantics across different dimensions of your latent space. As I've shown you here, like this space was about slanting ones, and this space was about 9, 7, and 1. So you can enforce a little bit clearer distinction of semantics between different axes. Like some axes will be only about digits, some axes will only about style, some axes will be only about brightness, some other dimension will be only about, I don't know, like size of the digit, something like that. So if you want to enforce that kind of like explainability or like disentangling of dimensions, then you can turn to these literature. Right, so I think this is it. Thank you for staying and thank you for coming to the class, even though this is a national holiday. I really appreciate your effort into commitment to your class, commitment to this lecture course. If you have any question, please let me know. We will revisit this VAE thing and variation inference thing when we study diffusion models, which will come in the very later phase of this course. All right, thank you guys. Yeah, thank you very much. So I'll stick around maybe 10, 20 more seconds just in case someone has a question. Otherwise, you can leave. Oh, by the way, I'm gonna announce this on Calamus as well, but the practice session will also be conducted as usual, even though yeah, October 3rd is a 개천절. I'm not sure what that is, what you call that in English. But anyway, October 3rd is another national holiday as well. Which is coincidentally, there are a lot of holidays in our like in Tuesday and Thursday this year. But anyway, but we'll conduct the practice session no matter regardless. So please come. Sorry if the assignment going to be released soon. Actually, not really, because we have three more classes to go. I think two more classes to go before project one. But yeah. So we will release the spec on the week of the midterm week, Tuesday, and then you can start coding. Right. Apart from that, I guess there are no questions. So how long will the due be? Due will be for 24 hours. So if you're please, if you are interested in like details of the projects, you can ask the LLMTA. But as I said, it'll be a 24-hour project, individual effort, and we'll give you the specs on Tuesday, the usual 10:30, and the 24-hour will begin at 12 p.m. And as I said, I assume it'll take you less than 1 hour because, as I said, you can use whatever tools that you prefer. Claude 3.5, GPT-4o, GPT-o1 preview, whatever you want. Okay. All right. I don't think there are any more questions. All right. Thank you guys for coming and see you guys next week. And don't forget to come to the practice session this Thursday. All right. Thank you guys. Bye-bye.